I drank a beer. I drank another beer. 3 beers. 4 beers. Oh no. 5 beers. Oh no. 6 beers. 7 beers. 8 beers. 9 beers.
Okay, so the Beer-Lambert law is a law that states that the absorbance of a solution is directly proportional to its concentration and the path lengths of the light through the solution. All of which can be shown in the following formula. The A stands for the absorbance, the amount of light that is absorbed by the sample. The epsilon is the molar absorptivity, which is basically also known as the excision coefficient sometimes. Basically, it is a constant for a specific substance at a specific wavelength. The L, sometimes called a B also, is the path length, which is the distance that the light travels through the sample, usually around the width of the cuvette. And then the C, which is the concentration, which is the amount of the absorbing substance in the solution. The relationship between the absorption and the concentration is linear, meaning that as the concentration of the absorbing substance increases, the absorbance will increase proportionately. So if we fail to zero the machine with a blank, then it will result in an artificially high absorbance value, which we very obviously do not want. Now that we have a pretty decent understanding of all of this, let us go ahead and take a look at the technique.
We begin by preparing our cuvettes. Each solution is poured into its cuvette, making sure the liquid level is high enough for the light path, but not so high that it could spill. We also prepare one cuvette filled with distilled water, which will be used to zero the spectrophotometer. We open the app on the screen, and then before placing any cuvette into the machine, we wipe the clear sides thoroughly with a lint. Free tissue to remove fingerprints, dust, and other things. The frosted or labeled sides should always face left and right, so the clear sides align with the light beam. And then we open the lid and insert the water cuvette, and then we close the lid and press 0 to calibrate the instrument. Once the machine reads 0, we open the lid, remove the blank, and then we prepare the first sample by wiping the clear sides again, ensuring they're clean, and placing the cuvette into the spectrophotometer with clear sides facing the light path. We close the lid and press scan. When the reading appears, we record the absorbance value, then we remove the cuvette and clean the area if there's any solutions that has spilled, and then we repeat the process with each remaining sample.
Let's now discuss why we would scan across all wavelengths. Our first reason would be to detect any impurities in the sample and to determine if there are one or more compounds present. Our second reason is to find which wavelength absorbs the most light. This wavelength is considered to be the lambda max. Once the lambda max is found, future measurements can be made at this wavelength to ensure maximum sensitivity and accuracy in concentration calculations using the Beer-Lambert law as previously stated in the video before.
From our notebook, we collected absorbance data from our set of solutions, a blank, 2 unknown solutions, and a bit of waste in between the two. Unknown 1 peaked at around 550 to 600 nanometers, which means it absorbed more around green or yellow in the UV spectrum, which leads to a magenta/pink color. Unknown 2 had relative peaks around 550 to 600 nanometers and another at 650 to 700 nanometers, which absorbed yellow and red. This left us with a transparent color of blue/cyan color. The blank was flat all around, which obviously led to a colorless, and our waste was similarly flat, which also left us with an almost colorless solution.
Clean up, everybody everywhere. Clean up, everybody do your share. Clean up, everybody everywhere. Clean up, everybody do your share. Clean up, everybody everywhere. Clean up, everybody do your share.
Look at our very clean lab bench. So cool. So epic. So amazing. So spectacular.